Okay, so what we're going to be talking about here is what I like to refer to as the area so far function. Okay, so the area so far. As you can see, we have the graph of the line f of x is equal to 2x. So here's our function, f of x is equal to 2x. And we have the graph of that line actually up here on the board. You can notice that with my y values, I'm moving by 2 every time. So you can see the 2, 4, 6, 8, 10. And then with my x values, I'm only moving by 1. Okay, so remember those heights each count for 2 apiece. And then I have a couple of different integrals up here that I want to look at. And then we're going to try to get to a general form. Okay, so the first thing I want to talk about is this first one right here. The area, right? Remember, an integral is the area under a curve. So we want to know the area between 0 and 1. Okay, the area between 0 and 1. And we've been doing, shapes with geometry, right? We've been able to find the area under a curve using geometry. And so I'm going to employ that same skill right here. And if we do that, okay, if I wanted to come up with this integral right here, if we were just strictly speaking in geometric terms, what would you say this right here is? It would be 1/2. What's the base? If I was going from, the area from 0 to 1, so that's this piece right here. So what would my base be? Yeah, 1. And what would my height be? Yeah, the height would be 2. Remember, each one of those things actually counts as 2. Okay, so if I multiplied those together, what would I get for the area? Yeah, I'd get 1. Okay, and then you can see for the second one here, I expand it to the area from 0 to 2. So that x value 2. And now I want to know the area under the curve, right, from 0 to 2. And once again, I have a triangle, so this will be 1/2 base. And what's the base of this one? Yeah, the base is 2, but now the height is how much? 4. Okay, so what's my area? Okay, so the area of that one is 4. All right, the next integral we have is from 0 to 3, so I'm starting at 0 and I'm going to 3. Okay, and I want all of that area under the curve. And you can see, once again, the area from the curve to the x-axis just creates a triangle. So for this triangle, it's 1/2, and now my base is 3 as I moved out. And what's my height? Yeah, the height is now 6. So how are you getting that height, by the way? I mean, you can look at it on the graph, but another way to get it is to take that x value and do what with it? Plug it into the function. Okay, so this right here gives us an area of 9. Yeah. And now the last one right here, and then we'll actually get to the important stuff, right? This is from 0 to 4. And so if we talk about this area right here, okay, area from the curve to the x-axis from 0 to 4, it's a triangle, so it's 1/2 base. And now the base is 4 because it goes from 0 to 4 times height. And the height of this thing is 8, you can see there. And so if you multiply those together, 1/2 times 4 is 2 times 8 gives us 16 as the area under the curve. And so I'm just trying to point out that we end up with a triangle every time. If we go from 0 to whatever number, then we end up with a triangle every time. And so now you can see this this other integral I have written down here. And you can see that it's the area from 0 to x. So what I want to do now is I just want to generalize this and talk about it. And then hopefully there's kind of the big reveal coming after that, right? Okay, so if we go from 0 to x of f of x, we know we're going to have a triangle, right? Is everybody okay with us having a triangle? So the area of this triangle right here, we know we've seen the pattern again and again. It's 1/2 base times height because this thing's always going to make a triangle. What is the area of this triangle going to be? It's going to be 1/2 base. Now, how am I getting my base? What's my base going to be? X. Yeah, it's just whatever the x value is. In this case, from 0 to 1 was 1. 0 to 2 was 2. 0 to 3 was 3. 0 to 4 was 4. Right? So it's just if I start at 0 and then I move out, right, however far I move, whatever that x value is going to end up being my base. So that's my x value times height. Now, in a function, where do you get a height? How do you get a height from a function? It's the y value, right? So, but in reality, the way you get a y value is you take an x and do what with it? Plug it in. That's exactly right. So, if we wanted to talk about the height of this function, it's always what? Yeah, it's always 2x. Right here, you know, it was at 1, our height was 2. At 2, the height was 4. At 3, the height was 6. At 4, the height was 8. So it was always just 2 times whatever that x value was. So this is 2x. So if we want to be able to find the area from 0 to x for this function f of x, then what we have is 1/2 times 2x squared, right? I'm just multiplying these two x's together. And then we could say the area from 0 to x of f of x dx is equal to x squared. Huh. So the area so far function in this case is what? What do we get whenever we did that? That tells us the area from 0 to x. What function does that? X squared. Ethan, did you have something you wanted to? Yeah, it's the antiderivative of this. It's the antiderivative of f of x. That's what this right here is. So, and this is not an anomaly, okay? This is in every case. The function that will tell you the area under a curve so far, the area so far function, as I like to call it, is the antiderivative. So some of you guys have been asking the question, you know, we've been working some indefinite integrals. We've just had stuff like this. And, you know, I put something under there like 3x squared dx. And you guys are saying, oh, it's x cubed plus c. That's our antiderivative. And then in other cases, I've given you problems like this from 2 to 5. We'll just say x dx. And, you know, all right, so this is now an area problem, right? And so you would use geometry to find the area under that curve is all that we've done up to this point. And I know several people asked, why is the antiderivative, you know, whenever we have an indefinite integral up there, we want to take an antiderivative. Why is it the same sign for the antiderivative and for the area under the curve? And the reason why is because what an antiderivative gives you is area under the curve. That's what it does, okay? So that's a really important note. So if you don't have that in your notes, you want to write that down. Okay, an antiderivative is an area so far function. It will give you the area underneath whatever curve you're talking about from 0 to an x value. Okay, so from 0 to an x value. So let's consider this same function we had from 0 to x, okay, of 2x dx. Then all we would need to do would be to take the antiderivative, right? And what would that give us? It would give us x squared. Okay? Now, what if we wanted to go from 0 to a of 2x dx? What would we do? Well, a could be any number whatsoever. It would be x squared, but then we need to plug in what? A. It needs to be evaluated at a, okay? Because look back at this one right here, okay? For this one right here, let's just consider the fact that we said, let me see if I can get a different color up here, right? This was the area so far function, okay? In this integral right here, what was our, this one, right? What was our x value? 1. Plug it in. What's 1 squared? That's the answer we got. And this second one right here, what was our x value? It was the 2 right there. What's 2 squared? That's the answer that we got. And this one, it was 3. What's 3 squared? That's the answer we got. And the last one, it was 4. And obviously 4 squared is 16. Right? So all we need to do is we need to take that x value and we need to plug it into the area so far function, right? That's the whole idea behind area so far. If you want to know the area from 0 to 6, then what you do is you get the area so far function, which will tell you the area from 0 to a certain point. And if you want to know the area from 0 to 6, then what do you put into the area so far function? 6. That's exactly right. And when you put the 6 in, it'll say, hey, this is the area from 0 to 6. There it is. It'll just give it to you, okay? So now I'm using a variable. We want to know about the area from 0 to a. So I'm going to take this x squared right here, and I'm gonna write this like this as far as notation goes, okay? So this is our area so far function, and we want to know about the area all the way from 0 to a, right? And so all we do is take that a and do what with it? Plug it in. So the answer would be a squared, right? That's what the area would be a squared. Now the area from 0 to b of 2x dx, what would that be? X squared evaluated at b, so the final answer would just be b squared. Very good. Yeah, yeah. Okay, so notice that the area so far function, though, whenever we take an antiderivative, what it gives us is the area from 0 to a certain point, right? So if we had a graph here of this function, and I'm just going to graph, a rough sketch of 2x. It looks like this. And let's just say this was a. And so this first equation here would give us the area from 0 to a, that space in there. This second here would give us to b. Let's just make b a little farther out, right? Okay, and now this is where our integral properties come in handy, right? Because notice this only tells us about the area from 0 to a and from 0 to b, but what if I wanted something crazy like this, right? What if I wanted to know the area from a to b? What if I wanted to know the area from a to b? How could I get the area just from a to b? Huh? Well, it would change my shape if I did that. Okay, but here's the easy thing. Think about properties of integrals. If I know the area from 0 to b and the area from 0 to a, right? Because the area so far function can give us both of those numbers. It can give us 0 to b and it can give us 0 to a. So how do you get from a to b? You just take, we want to get from a to b. This is what we're looking for, right? So what you do is you just take all of b, which would be the blue stuff in here, and you take away all of a, which is the green stuff. So if we do the blue minus the green, then we'll just get left with the area from a to b, right? So all we need to do in our minds, right, is the integral from a to b of 2x, sorry, let me start at 0. From 0 to b of 2x dx minus the integral from 0 to a of 2x dx. And what this will give us, we already know this first one. What is the integral from 0 to b of 2x dx? It's b squared minus, what's the second one? A squared. So, and all this is doing, I hope you can see this, is finding the area from 0 to b and then taking away the area that goes from 0 to a, right? Is everybody okay with that? Okay. So, in general, okay, so let's just make a general form of this. The integral from a to b of f of x dx. Okay, so we're just going to generalize right here, okay? We're going to generalize this. The integral from a to b of f of x dx. What would we need to do? Take the antiderivative. Now, the antiderivative is actually denoted by f of x capital, right? So capital F of x is the antiderivative. Okay, and I'm going to add this little piece of notation in here. Evaluated from a to b. Okay, so that may be new for you, okay, but evaluated from a to b. So the antiderivative evaluated from a to b. But now just think about it in the context of what we did before. Okay? Think about it in the context of what we did before. We took the antiderivative or the area so far function and we found out the area from 0 to b, right? So how do we find the area from 0 to b? We plug b where? Into this, okay? So we want f of b minus, right? Because then we had to take away all the area from 0 to a. How did we get the area from 0 to a? You take a and you do what with it? Plug it in. So I'm going to rewrite this just as this of f of x dx is equal to f of b minus f of a. Okay, so capital F of b minus capital F of a. And this right here, okay, this right here is extremely important. This has a name. It's so important. This is what it's called. The first fundamental theorem of calculus. Okay, that is actually so fundamentally important, right, that it has actually been given the name the first fundamental theorem of calculus. Okay, the first fundamental theorem of calculus. Ethan, go ahead. Don't we need to know if B or A is bigger? Not really. Okay. If A was bigger, you would get a negative value, but remember our property of integrals, that the integral from A to B of f of x dx, okay, and in this case, we're assuming that A is smaller, right? But if A actually ends up being the larger one, let's just say that that ended up being 3, okay, from A to B. But if for some reason A was the larger one, in reality, what would be happening is you would be going from where? From B to A of f of x dx. You'd be going backwards. But this is, you know, the integral from A to B, or from B to A, is the negative of the integral from A to B, and so it would end up being negative 3. Remember that property that if you flip the order, you get a negative instead of a positive, right? It just changes the sign. Well, if we flip the order and we make the big number on bottom and the small number on top, it'll just change the sign of whatever we had before. It's perfectly fine. It'll all work out. It's kind of all taken care of in there. Okay, let's actually work a couple of these. Okay, so we're going to take the integral from 2 to 3 of, and I pick 3x squared dx. Because there are just a couple more important little things I want to show you about this. All right, the first thing that we need to do is we actually need to take an antiderivative. So what's the antiderivative of 3x squared? Yeah, x cubed plus c. Okay, and so now this is what we have, and let me actually write it. This will be some good notation for you guys. X cubed plus c, right? And what we do is we usually write a 2 and a 3 on the outside, and that's our evaluation right there. Okay, so we want to evaluate from 2 to 3. I had some professors in college who wrote them at the back, okay, at the back of the brackets, and some professors in college who wrote them at the front of the brackets. That is not really the main idea, okay, but you can kind of do it either way. I'm trying to see what your book does. Which way does your book write them? I'd like to keep up with the book, but I did have, like I said, professors who wrote them both ways in college, and so it kind of made it confusing for me. I never can remember which way you're supposed to do it. But in the book, I think I got one here. Yeah, they write them in the back in the book, okay? So we can put them in the front, we can put them in the back. If you want to, you can put them back here from 2 to 3. Either way is fine. Okay, now there's one more important thing that we need to do. Okay, so now what we want to do is we want to plug in, what's our B in this case? 3. Okay, so we're going to plug 3 in. Let's see. So that right there is f of B, right? This right here. Minus f of A, which is what? 2. So now we're going to plug in the 2. And this is an important concept. What's 3 squared? 27 plus c. And then 2 cubed is 8. Okay, but now this negative sign right here is the most important thing I want to make sure we get across, is that it has to be distributed. So minus 8 minus C. Okay, minus 8 minus C. And look what's going to happen to these two C's. What's going to happen with them? They cancel out. And that will happen every single time. Okay, because of the way this thing is set up with f of b minus f of a, the C's will cancel one another out every single time. Therefore, do you think we have to include them? No. Okay, now this is called a definite integral, right? Because we're going specifically from 2 to 3 so we can get a numerical value. Whenever we have an indefinite integral, if it was just this, then what we can do is this still asking about area under the curve, okay? But what we can do in this case, since we don't have specific places, is we give it the function. We say, hey, if you want to know the area under the curve, use that function. It's kind of like a derivative. You know, you can evaluate a derivative at a certain point and give me a number, right? It's 5, okay? Or you could say, this function will give you the slopes, right? So when it gives you a derivative, if you're not looking at a specific point, you give a function and say, this is the function that will tell you about all the slopes. Same idea here. If we're not looking for an area from a specific point, right, then what we can do is we can give a function that will give area, okay? And so whenever you have an indefinite integral, you need to include your C, okay? But in these, the C's will cancel out every time whenever we're going through the process because we have the two functions being subtracted, f of b minus f of a. So we can leave it out in that case. Okay, and let's finish this thing up. Right now what we have is 27 minus 8. That's what's left. And 27 minus 8 is 19. 19 is exactly the amount of area under the curve. Okay, that is perfect, spot on, precise. Okay, the area under the curve 3x squared from 2 to 3 is exactly 19. Okay, 19 square units. Cameron. How do you know that the C's are the same value for the constants? Because it's the same antiderivative, okay? So it's the antiderivative of 3x squared both times. So since it's the same function that you've taken the antiderivative of, the constants are the same constants, and so they'll cancel each other out every time. Okay. All right. Now, there's one other thing I want to make a point about. Oh, yes, that's it. I want to relate this to what we've done with Riemann sums, and then we'll just work some practice problems, okay? So one more big concept in relating this to Riemann sums. We're talking about the area from A to B of f of x dx, okay? And in specific, I want to relate this to our rectangles, right? So a LRAM, RRAM, MRAM, and I'm just going to give myself a random curve right here, okay? So from A to B, and this will just be, I'll relate them a little bit. This won't be an exact science that I'm doing. There are ways to do it more precisely, but I just kind of want you to see in general what we're going for, okay? If we wanted the area from A to B and we were going to do Riemann sums, we could use a LRAM, MRAM, RRAM, right? Whatever you want to use. But what I'm going to do is I'm going to set it up like a LRAM, and I'm just going to I'll try to use like 3. Let me see if I can just at random draw 3 without too much trouble here. Okay, so there would be my LRAM, right? This could give me an LRAM. A left-hand rectangular approximation method could be used to guesstimate, right, approximate the area under this curve. And so if I did that, okay, how do I get the area of each of these rectangles? Okay, so how do I get the left-hand value? Yeah, whatever this function is, f of x. In order to get the height right here, I need to plug a in. So this will be f of a times, now how do you, for a rectangle for area, we got to get a height and we have to have a base, right? So this will give me my height, right? The function will give me my height, but how do I get the base? Okay, so b minus a over 3, okay, because we wanted 3 rectangles. But what is this really calculating? It's calculating how far we've gone from here to here, right? So can you simplify that for me? How far we've moved from here to here. What is that? In the most basic of terms. Delta x. It's how much our x value has changed. If this was, it looks like a 9 already, so I'll just say it's a 9, right? And this was 10. What would you say this right here is equal to? 1, because the x value changed by how much? 1. So that is really just the change in x, okay? So, plus, and what would you do? F of, now to get the second height, you would use this next point right here, okay? So I'm just going to call this next spot right here, I'm just going to call it C, okay? So, and I have B at the back. That's the only reason I'm using a C instead of a B right now. It would be F of C times delta x plus, and I'll call this one D, F of D times delta x, so on and so forth, right? So this is all that ends up happening, okay? What do you end up doing with all of these? With all of these different areas, you do what with them? You add them together, okay? So this is just a way that it could be written, right? We want to sum up F of, I'll just call it x times delta x, right? So F of x is going to give us our height, okay? And now, let me just keep using delta x for now, right? So delta x times the change in x. So that'll give us a rectangle, right? Okay, so we want to add up all of those. So we want to sum up all of those rectangles for every x value where x is in between, let's say, some value a and b. Okay, and this is not an airtight way of doing this, but I just want you to kind of get the general concept, okay? Now, remember, this was what for our rectangle? It's the base. This was what for the rectangle? Now, how can we make a Riemann sum more accurate? How can we get them to be more accurate? Well, I got 3 rectangles right here. So what is this right here? It's extra, right? What is this right here? Extra. Yeah, it's extra. And this is not enough. So one of the ways I could make this more accurate is by using more rectangles. Say I added in 6 rectangles instead. Look what it does to the amount of waste that we have. Yeah, it makes it less. So one of the ways that we can improve a Riemann sum is by doing what? Adding more rectangles. Which means what has to happen to my change in my x value? It gets smaller. So what if we let delta x get really small? Like infinitely small. Then how many rectangles will we have? An infinite number of rectangles. And if we used an infinite number of rectangles, what do you think will be true about the area that we find? It will be exact. Okay? So here's what we're trying to do. Whenever we write an integral, this is what we're saying. The function is going to give me the height. And I want my delta x to be extremely small. Do you know how we denote changes that are really, really small in calculus, infinitesimally small? Dx. And we want every single possible rectangle all the way from what? From A to B. That's the way you need to think about an integral, right? That's the way you need to think about a definite integral. It's an infinite number of Riemann sums from that area A to B where f of x, the function, is giving us our height every time. The function is always giving us the height. But our changes in x are so infinitely small, right, that we're going to get an infinite number of Riemann sums and then, therefore, an exact answer whenever we get to the end. Okay? That's how this kind of works out. That's the best way for you to think about it. This is an area, right? This is a bunch of rectangles, base times height. Okay? That's what we have whenever we're working these. Okay, so let's work. So hopefully that helps you kind of conceptually be able to lay hold of this. And so let's work just a couple of more problems together. Let's take the integral from 0 to 3. or sorry, from 1 to 3 of x to the negative 3/4 plus 3x to the 5/3 dx. Okay, so here's our function. That's our height. Dx is our base. So we're literally getting an infinite number of rectangles in between 1 and 3. And there is a way to take an integral using a limit as x approaches as n approaches infinity, for n being the number of rectangles that you take. There is a way to take integrals in that way. It's outside of the scope of what we want to accomplish, but if you want to go home and look at that, it's in your textbook. You can look at it and learn more about that if you'd like. Okay, so the first thing I need to do here is actually take an antiderivative, right? So what is my antiderivative going to be for this thing right here? Okay, so this will be x to the 1/4 power, and it will be multiplied by 4. This is going to be x to what power? 8/3. So then we're going to multiply it by the reciprocal, which is 3/8. Okay, so there's our antiderivative, and we're going to evaluate this thing from 1 to 3, right? Evaluate it from 1 to 3. Oh, thank you very much. This 3 was already there in the front. Okay, so this thing up top should be a 9 instead, right? That should be a 9. Okay, so the first thing that we're going to do, we got to evaluate this thing from 1 to 3. So what goes in first? The 3 goes in first. Yeah, the top actually goes in first. This is 4 times 3 to the 1/4 plus 9/8 times 3 to the 8/3 minus, and then we plug in our 1, 4 times 1 to the 1/4 plus 9/8 times 1 to the 8/3. Why no constant? That's exactly right. It would cancel out, so we don't need it. Okay, so this is going to be kind of an ugly fraction whenever we get done. So will somebody just run this through in your calculator and give me each individual piece. So somebody plug this piece right here in and give it to me in a fraction. Okay, so 4 times 3 to the 1/4 plus 9/8 times 3 to the 8/3, and see if you can give me fractional form of that. Anybody got it? Will it come out in a fraction? You could, yeah. Well, we actually want to get a numerical value. So what did you get for this right here? Just, you can give me a decimal, that's fine, and you can round it. But somebody plug it in and tell me what you get. What'd you get, Taylor? 26.3. All right, so can I get somebody to confirm that? 26.3. Okay, and then this back one right here is 4 times 1 to the 1/4 plus 9/8 times 1 to the 8/3. What'd you say? Yeah, 5.125. And now if we subtract those, what do we get for the answer? $21.175. Okay, so 21.175. And in general, okay, those will work out in a similar way, right? So I'm going to stop the video, and then we can work a few more problems together in class, and then, but they'll all work in general in that way right there. So that's kind of the blueprint for how to be able to do these.